Algebras. Welcome to your Chapter 12, Lesson 3 notes. We're talking about exponential growth and decay using our formula for a second day. So let's just review the exponential growth formula, the exponential decay formula, and my general plus and minus, how I kind of think of it, right? So the general formula is y equals a times 1 plus or minus r raised to the, we'll put t because this is a t right here, t power. And that is interchangeable with x being there, the thing we're going to plug in and then evaluate, right? For the growth, it's when you use the plus sign in the middle. And for the minus, it's when you use the decay, or for the decay, it's when you use the minus sign in the middle. So this is a pick or choose depending on the situation. So growth is you're increasing the value or the number. The decay is you're decreasing the value or the number or the amount of things that you have, right? So this plus or minus is on either or situation. It's not both. Okay. One or the other is happening. Can't be both at the same time. Now, what do each of these variables in here mean? A is the initial value, also known as the y-intercept. Okay. A is the initial value, also known as the y-intercept. The R is the rate of change. And I'm going to put under R in decimal form. So if you're given your rate of change in percent form, you must make sure it is converted into decimal form. And then the T is the X value or time, amount of time that has passed. That is the variable we'll know and test to find the matching Y, which is the total or end amount. The thing we're looking for that matches this. Okay, that's what that Y is. So, of course, what I have here to just quick review the types of word problems where we looked at this are these two different scenarios where on the left side, I'm increasing the population of a city. So I use the plus sign in my formula and add these two values together because I have a greater than 1 base, that's going to be an exponential increase or a growth. And then if I know my time, I substitute that in to know a population. Okay. And again, if we're talking about whole people or animals or fish or any of those things, right? That's whole numbers. If we're talking about like the value something is in dollars and cents, then you can round to the nearest hundredth, right? And do dollars and cents as your value. Okay. Over here, we're talking about the population of a city decreasing. And notice we use the minus sign when we're decreasing. Okay. So we still plug in our A and our R into the general formula. You can, of course, actually do the subtraction here. I didn't in the last video because really I was just plugging into my graphing calculator. I didn't need to do that. That was just one more step that my calculator is going to do that for me anyway. But the reason I do it here and the reason we show it here is because look, that's a value that's bigger than 0 but smaller than 1. A value between 0 and 1 as your base on your exponent, that's a decay function. So that's an exponential decay function. So that's the reason that I really wanted you to see that. Okay. This is where we're going to talk today a little bit about going backwards with that rate to know, going backwards with that total base to know what was the rate on a question. That has a tendency to be what the Regents asks. That's one of the things we're going to look at momentarily. But what I want you also to notice about these two different problems is that the initial value from here increased for my final answer, growth function. The initial value from here decreased for my final answer, decay function. Okay. quick review of what we've already done. All right, next. An aptly timed real life function application with our formula. Interesting. This thing called the coronavirus, an outbreak, is an ongoing public health concern. Didn't think I'd be saying that this almost exactly a year from when I made this up, but here we are. So, as of March 27th, 2020, over a year ago for us now, 25,237 people have died from the virus worldwide. We know what the answer is at this point in 2021. So, yeah, since we're way over 1 million now, it's gotten pretty rough, huh? Let's look at this like mathematicians. Okay? Let's analyze this as to why do we study exponential growth and decay? And this pandemic is a perfect reason why you need to understand what exponential functions are doing. So we can express the coronavirus deaths for the first month as this equation: y equals 17 times 1.18 raised to the x power. How many people initially died? What is our A value? 17. What is the growth rate of the virus? Now, this is the thing I haven't talked about with you yet, as to taking a base where the 1 has been added or subtracted with your rate in decimal form and finding what the rate is. So extracting the rate from something that's already been combined. It's easier in a growth function than it is in a decay function, and I'll show you why. In this case, we know this is a growth function because A, we're living it, and B, this is a value, this is a base value over 1. So that means that what you had is 1 plus a rate equaling 1.18. So all I need to do to figure out the rate is subtract 1 from each side, and that will leave me with the rate. And what's 1.18 minus 1? It's 0.18. That means my rate is 0.18 or 18%. 18% growth rate. Scary when you hear it that way. Does this situation represent growth or decay? Well, we've already answered that. The base is greater than 1. This is growth. Now what we're going to do is we are going to plug this into our graphing calculator, and we are going to use this to model what would have happened if this continued to be our growth rate of the function. Okay? So let's do that right now using our graphing calculator. Okay? So this will be the first 30 days, and we're going to go every 3. All right, so let's go to y equals. Oh, we clearly just used this in the video. Not using my graph right now, so I'm going to just make this bigger so we can see what's going on here, right? So I'm going to plug in my function, which is 17 times 1.18, end parenthesis, caret, x. Okay, and this x is representing days. So 0 days have passed, and there have been 17 deaths for this particular time period that we are looking at. Okay, that's at this start, if this is our start of time 0. So now what we're going to do is press second and graph to look at the growth function. And remember, we're talking about human beings, so we're talking about whole people when we decide to put our numbers down. Now notice that my table on here goes by 3s, and so I want to go by 3s on my x's. I can easily change what my table is going by for x's by pressing second and window. The table start is going to stay 0, but I'm going to head down here to delta table. So the triangle stands for delta, and then Let's change this from 1 to 3. This means now my table is going to go by threes. So I'll be able to see exactly the values that I'm being asked for right here to fill in. Okay. So remember, this is going by threes. Now let's get our matching Y's. So of course, day 0, 17. Day 3, notice I have taken my cursor, I've put it to the right, and I've put it on my value because I'm going to need to see my decimals to be able to round up or round where I am, stay where I am as my value. And in this case, my value for deaths on the 3 days later is 28. 27.9 rounds up to 28. Then I arrow down, and now I've got 46. And then I arrow down again, and I've got 75. That stays put because of the decimal next to it being 0.4. And I go one more. Oh, that's going to round up to 124. And remember, this is a model, so that's why it's not whole numbers. Okay, this rounds up to 204. This is how many people are now dying each of these days. Kind of think of it that way. 18, we're now at 334.4, so we'll stay at 334. Arrow down again. 550 because we got 549.5, so that's going to round up to 550. 24. 903. 902.8 rounds up to 903. 27. 1,483.4, so 1,483 it is. And the last one we're asked for in our table, 2,437.3, so 2,437. Okay. We're going to get these on our graph in a sec, but I just want you to kind of, this is total deaths. I had said that incorrectly. I had said it per day. Just reading it. Yeah. Okay. So total deaths so far. Got it. Okay. So this is the trend that we were seeing in March of 2020. Okay. So let's graph this trend using this is our day number. And we, of course, know we're going by threes. So we're not going to have those in between days, right? And then this is our death totals. So 0, 17, well, that's yeah, best we can do is kind of, because our scale on our Y's is by hundreds of people, right? That's kind of the best we can approximate. These values right here, these actually are at the values we want to be at. So these dots can represent 3 and then 6 and then 9 and then 12. And so when we're looking at the odd ones, we can figure that out, right? So now we want to go up to 328. Well, that's really not going to have moved at that point up too much. And 46, same. And 975, we still haven't hit 100, so we're just getting closer. And then 12, 124. Okay, so that's still only a little bit over 100. And then 15, 204. Well, that's just a little bit over 200, so let's just put that right there. 18, 334. Okay, so here's 300. Arrow across right kind of here, third of the way up. 21, 550. So go up to 500 and then halfway between 500 and 600. And then 24, 903. So just put it right on the 9 there. And then 27, 1,483. That's closer to 1,500. Real nice and close to 1,500. And then 30, 24, 37. So it's about a quarter, or excuse me, about a third of the way to 25. And that is why social distancing was put into place right there. And if we hadn't begun that, how many people would have died after 60 days? Okay. So what was that trend looking like, and how scary was that trend for us to really say, we better stop, we better, well, mask wearing came in after the fact, but we better do what we can to stop this, because another month of this trend would have led us to 349,437 deaths. And as it is, we have far surpassed that, but not in May of 2020. It took a lot longer to get to that point. But had we not social distanced and changed this equation and trend, here's where we would have been. And this is why it's important to understand what exponential growth and decay truly look like. Okay? Especially with viruses, plagues, and whatnot, pandemics, as it were. What did we say that number was? 3,400 and, 349,437 people. Okay. And again, all this using the model we had come up with in March of 2020. This is how we use exponential growth and decay to make predictions. All right. Well, let's back away from the heavy. And let's look at some former Regents questions where we are asked about situations like this. So a couple of the Regents questions are kind of cool in that they actually just kind of hand us the equation and ask us about it instead of asking us to use it. So it's just, if I hand you this exponential function, this growth function, or this decay function, can you interpret what's going on? Okay. And so I'm going to do one, and then I'll kind of leave a couple of these for you to try and see how you do. But I'm just going to model number one for you. The breakdown of a sample of a chemical compound is represented by the function P of T equals 300 times 0.5 to the T, where P of T represents the number of milligrams of the substance and T is the time in years. In the function, explain what 0.5 and 300 represent. They're telling you what P of T and T represent. So what do those two numbers in the function mean? Well, 300 is your A, and your 1 minus rate is 0.5. So if you want to isolate your rate, you need to subtract 1 and then divide both sides by -1. Now, this one's a lot easier to see in your head, but I'm going to show it to you on the graphing calculator anyway, in case you run into one that's not as easy to see in your head. So 0.5 minus 1 leaves me with -0.5. And now, because I'd have a negative r left, if I just divide this by -1 to get r all by itself, I'm left with a rate of 0.5. What this is telling me, as far as this goes, is for this chemical compound, the initial amount of substance was 300 milligrams. That's what the A is, the initial amount before we started. And then the 0.5 is the rate of decay of the substance over T years. Now, how do I know it's decay? Well, because in the final function, this base is between 0 and 1. And a base that's less than 1 is a decay function. Okay? So since this is a Regents question, and notice it's not a multiple choice, you need to actually write out in sentences your explanation for this. Okay? So 300 represents the initial amount of the chemical compound, let me spell that correctly, and 0.5 represents the exponential decay rate of the compound, spelled it correctly this time, over time. Take a second to make sure you have that fully written out. Practice writing sentences like that. Notice where I got my information from, right? Breakdown is indicating to me that this will be decay. Chemical compound is the substance in play, right? The function is right here. And I analyzed that function. I was told what P of T was, and I was told what T was, time in years. Explain these, explained. Full sentence. I'll have you do number 2 in a second, so hold off, and when we pause from doing this, you'll try number 2 on your own. Let's try number 3 together. The function V of T equals 1,350 times 1.017 raised to the T power. Represents the value V of T in dollars of a comic book. Oh, T years after its purchase. Cool. So V of T is the number of dollars the comic book is worth, and T is the number of years post-purchase. Whoa, that's a lot of money for the initial purchase of the comic book, huh? What's the yearly rate of appreciation of the comic book? So I just said that, and then I never mentioned. Well, A is $1,350 initially purchased for that comic book. Whew. How to figure out the rate of appreciation. Appreciation is a grown-up word for growth or increase in value. And again, another way that I know it's growth or increase is this value is greater than 1. That says less than 1. How about I read left to right like a human? The rate is greater than 1. So because of that, the base is greater than 1. Let's call that a base. So because the base is greater than 1, I know this is growth or increase or appreciation. So now how do I figure out what that rate is? And it just says what's the yearly rate, so it doesn't mean it has to be in percent, right? So I take this rate, I take 1 plus R equals this rate. And now what I do to both sides is I subtract 1 from both sides, and my rate is 0.017, or move this over twice, 1.7% annual growth. Annual being another word for yearly. I'll have you guys try number 4. And then I'm going to try number 5. All right, so here we go. Milton has his money invested in a stock portfolio. Okay, typically with investing, we like that to be an increase, but let's read about Milton. The value V of X in his portfolio can be modeled by the function V of X equals 30,000. Whoa, Milton, good for you. That's how much you initially invested. Times 0.78 to the X. Oh, Milton. Where X is the number of years since he made his investment, which statement describes the rate of change? Oh, poor Milton. Is his investment growing? No. All right, no. Look, this is a value less than 1. Ugh. Poor Milton. Poor Milty. 1 minus r equals 0.78. We got to subtract 1 from this. So we take 0.78 and we subtract 1 and we get negative 0.22. And so if you divide that by negative 1 to get r as positive, you got a 22.22 or 22% decrease annually. Yikes. See how I figured that out? Figured out what that rate was? Or Milton. That's gotta hurt. Oof. All right. Pause it right here, guys. Let's have you try number 2 and number 4, having me done 1 and 3 and 5, and let's see how we do, right? And we shall be right back to check those answers. All right, guys, check your answers to number 2 and number 4, which I did in red so that you could see those a little bit better. Make sure you understand where both of my sentences came from and that yours are something pretty darn close with about as much detail. All of these things being former Regents exam questions, you can see how you can anticipate these questions about exponential growth and decay being asked of you. I want you to take note, only one of them was multiple choice. There's a good shot that you could end up with a 2-pointer like 1 through 4 that just has you describing what's going on in the equation, which would be awesome. Even the multiple choices, just having you describe what's going on in the equation doesn't even make you actually use it, right? So as long as you can look at it and say, this is growth, this is decay, this is the rate, this is the initial value, and here's what it means in the context, you're good to go. All right. Algebras. This has been a second day talking about Chapter 12, Lesson 3, Exponential Growth and Decay in Function Form. Remember, the plus is the growth, the minus is the decay, and yes, they must be one or the other in this case. Guys, I shall be seeing you soon. Of course, ask me for questions if you need help, and have fun. See ya.